Jaden, tell me it's number 3. The HCl nitrous acid. Okay. Good morning, sunshines. We're going to do some questions together. Have your stuff out. Okay, back with me. Thank you, thank you. Who are we missing? Oh, Marcus is taking his test. Oh, there's somebody else on. Who else isn't here? Yes, I need you to do that and we'll finish that in a second. Can you just catch up with us for a moment? Oh, yeah, okay, for a little bit here. Okay. Well, guys, welcome Mono Emily back. She's here. And we're just going to, make sure she catches up with the redox with us, okay? So, oxidation state 1, the first one I'm doing is number 3. And then we're going to go to acid-base ones, okay? So I've heard some good, aha moments, so I'm hoping that you got what you needed from me or from a friend, but make sure you ask as you need to, okay? So we have this big old reaction. What did you guys start with doing? I know I was saying oxidation state. So which ones were the ones that changed oxidation state? Nitrogen, which was a +3, right? And what over here? +2. And then the other one was iodine, -1 and 0, right? So as you went through and you did your little bracketed blah blah blahs, here's your nitrogen. What happened to it? So it lost, or it gained 1 electron. So you definitely see 1 electron from a +1 or +3 to a +2. And then the problem with the iodine is that initially you're just like, oh, it lost, or there's an exchange of 1 electron as well. But what's weird is this one's diatomic and this one's a singular. So you have to account for that overall. We're going to put a 2 in front of the sodium iodide to make it have 2 iodines so you can compare them in the same fashion, because you can't really half that one in half. So put a 2 here, and then if we have to change it, we will, but we shouldn't have to. We're just making it's basically like we're in our acid ones where we balance the non-H's and O's first. We're balancing the iodines first. So now iodine is balanced. So overall, from this iodine to this iodine, with 2 of them overall changing by 1 electron each, we have a total exchange of how many electrons? 2 electrons, right? So loss of electrons by 2. Okay. So then notice the electrons are not balanced. So what do you have to do now? Multiply the bottom one by 2, right? So that's this reduction is gain. So multiply this bracketed item by 2. So 2 nitrous acids, 2 nitrogen monoxides. Okay, and then this is the end of it, right? You're looking at the rest of it by inspection. Sodium needs a 2 in front of it because there's 2 sodiums over here. Iodine is good. Chlorine, I need a 2 over here to balance the chlorines out. And then how many H's overall on the reaction side? 4. How many H's over here? So add a 2 here. And then oxygens over here we have total 4. And over here we have 2 plus 2 is 4. Okay, so that's the only weird part when you don't have your individual redox items balanced initially. You might have to add a coefficient first. Yeah.
So when you do that?
When you're the whole process. So if I give you a question that says, so this would be this one. Balance this reaction.
And when you added
Oh, weird 2. Weird 2 is whenever the redox atoms are not already balanced by matter, like number of atoms. So initially I had 2 iodines. I had 1 iodine, so I had to make that 2 first before I could start looking at the multiplication between the 2 electrons.
So you have to balance first after sometimes?
Yes. But this whole scenario would be not in acid, not in base. It's just, here's a reaction, balance it. And like I said, most things are redox in nature. So if you have to balance by inspection, you can probably figure that out. It might take you 5 minutes. But if you can balance by oxidation state change, it might be a little faster route. It's kind of tomato, but many times we'll actually be able to solve it faster via oxidation state change. Okay?
Is there any sort of thing that you have to do because of that?
This 2? Just recognize that when you're talking about it now, you're talking about 2 iodines. each of them with an individual oxidation state of -1 to 0. So individually, the iodines are changing by 1 electron, but with being there two of them, we now say overall there was two electrons exchanged. It's just recognizing that as you write this right here. Okay, yeah.
Well, how is the 2 electrons at the top different from the 1 electron at the top?
They're not. So that's the point. We want the 2 electrons that are being lost to also be represented in the gain fashion. But this 1 electron that I pointed out was from the nitrogen of the 3+ oxidation state to the 2+ oxidation state. So since there's 1 nitrogen there prior to us balancing this, and 1 nitrogen there, there was a total gain of 1 electron, but we have to account for the fact there were 2 lost. So then we had to balance it with this 2 to indicate the equivalence of the electrons lost and gained, which this 2 here was why we added the 2's here to cause the overall charge and mass balance. Yeah.
So if we have a case like this, we just wouldn't touch the ones that were oxidized or like I wouldn't do that.
So if you didn't have a case like this, we wouldn't touch them until we found our multiples. Right. But in this case, we had to at least address the unbalanced atoms first, so we could actually get the full electron loss and gain. Okay. Yeah.
And if we were to do anything, we already like balanced, like if it was non-diatomic iodine, we would have to apply the same coefficient to the one because they both have the
Within our redox couple. Yep. All right. So 4 is similar. Yeah. 4 is similar with that 2 thing. So I'm actually skip 4 for a second. You guys, it's very similar to 3 with the 2 you have to include first on carbon dioxide. I'm going to go down to 5. So this, I think it's faster if I actually write this out for a second versus finding it in my notes. I'm trying not to write the coefficients as I go. Alright, it's going to get cramped over here. Okay, is that everything? Okay, so we're on 5 now, okay? So what was the what were the redox couples? Who was changing? Phosphorus was a what over here? A +1, and phosphorus was a what over here? A +5, okay? And then chromium was a plus what over here? +6 over here. And a plus what over here? +3, right? Because the chlorine was a -1, so this would be a +3. So those are our redox couples, right? So phosphorus is undergoing what? Say again? Oxidation by how many electrons? 4 electrons are being lost from a 1+ all the way up to a 5+. And then chromium, we notice first that they're not balanced. Okay, so let's think about those as we go. A single chromium has an oxidation state of 6+. A single chromium has an oxidation state of 3+. So it looks like there's a gain of 3 electrons, correct? But there's 2 chromiums doing that process. So we have to see the fact that this 2 is not balanced over here. So adding a 2 here will allow us to effectively talk about our chromiums. So the chromium overall exchange in electrons is what? Say again? Total overall chromium. 6, right? So 1 chromium went from 6+ to 3+, that's 3 electrons, and another one did the same thing, with 6 electrons. So we have a reduction of overall 6 electrons exchanged, and then I have 4 up here. What's my least common multiple? Say again? 12, and I try to do least common multiple, that way we don't have to reduce at the end, it's just extra step. So 12 is going to be the final, so I need to multiply this top one by what? And this bottom one by 2, okay? So let's go ahead and do the 3 first, because that one's pretty easy. It's going to be a 3 in front of the 2 acids here. And then how do you think I'll need to adjust for the potassium dichromate and then chromium 3 chloride? A 2 and a what? Well, so I want to put this 2 multiplier over here. And a 4. So I put that 2 there just to hold the balance of chromiums, but since I now have a multiplier of 2, I need to then multiply them both by 2 so that the charge stays balanced as well. So I need to account for both electrons. So this is not going to be a 2 anymore. This is going to be a 4. Okay, it's a 4. And then from here, you just have to balance, right? So phosphoruses are balanced. Potassiums are balanced, yeah or nay? Potassiums, I have 4 here, so I need 4 here. And then chlorines, I think I can see how many chlorines are over here. 16, so 4 times 3 is 12, plus 4 is 16. So where am I going to put 16 over there? On the HCl. So then I've got a lot of hydrogens going on here. So I've got 16 plus 9 is what? 25. And then I've got 9 plus, oh, hold on, what did you say? 25? 25 hydrogens over here. And then I've got 9. And then what do I need here? And 8 to get like 16 hydrogens, right? So that's going to give us our 16 plus 9 is 25 hydrogens. And hopefully our oxygens are balanced, but go ahead and check for me. How many oxygens are here? 6 plus 14 is 20, right? And then 12 plus 8 is 20. Score. Okay, so that one's a little bit more challenging. Yeah.
Why don't you only connect the phosphate and
The 2 phosphoruses?
because like not
Because what we, and this is in your video from yesterday, what we have to do is we assign oxidation states to every single atom, which takes a minute. So as we do that, and we notice that hydrogens are staying the same as +1s, and oxygens are staying the same as -2 for oxidation states, and potassiums are staying +1 for oxidation states. They're not involved in the redox part of this reaction. So we're looking only for oxidation state changes, which is from this phosphorus to this phosphorus. We'll get you caught up. Okay. All right. Let's do one more. 7. 7. So say these names for me as we go, just so you're practicing your nomenclature. On that, this one, nitrous acid plus potassium permanganate plus sulfuric acid yields manganese what? Manganese what? 2 sulfate plus nitrous acid, dihydrogen monoxide, and potassium sulfate. Okay. After you've assigned all your oxidation states, who's involved in the redox? Manganese is a what here? +7, and it goes to a plus what? So let's talk about this one as a separate entity for a moment. So this is an ionic compound, right? Cation, anion. If I were to split this, let me just get some space real fast. So if I were to split this in half as manganese 2, right, monatomic ion, right, and sulfate, you should now be able to really tell me, I know you assigned the -2 first for oxygen. This is technically its own ion since it's an ionic compound, right? We've got it together, but it's still an ion. So this one has to be +2 charge. And that's because this side, remembering, let me just scratch that for a second. Remembering sulfate has a -2 charge, right? Right? So sulfate has a -2 charge overall. This counters that to make it an electrically neutral ionic compound. So this oxidation state is the same as its charge. And then separately, our little finagling of the oxidation states will let us get sulfur. So this is going to be -2 for oxygen oxidation state. What's sulfur's? Say again? Plus what? 6. Okay, just making sure we're all good here. So that's a -8 plus 6 is equal to -2. So if you have an ionic compound, assign the metal its ionic charge, because it is a monatomic ion. It's just within a compound still. So this is going to be a +2. So I'm glad we went over this one. So this is +2. What's your nitrogen over here? Come on, give me some of the good stuff here. Let's get the charges. +3, and then over here, +5. Right? Who's feeling okay with assigning their own oxidation states? Like 90% of the time, you're okay. Right, so we'll practice with them, but it's gonna be basically involved in every question we do from here on out. Sulfur, yet again, do you notice that sulfur is still in the sulfate form, and sulfur is still in the sulfate form, and sulfur is still in the sulfate form? Sulfate itself is basically a spectator ion here, because it will be ionizing basically off of all of these compounds, so that's why it's not involved in redox, because it's just not changing at all. And then a lot of our hydrogens are the same way. Our oxygens are still involved with I see permanganate here and nitrate here, but overall the oxygens are not changing either. So our nitrogen is doing what? Say again. 3 plus to 5 plus. Oxidizing by how many? 2 electrons, and then our permanganate is changing by, so it's gaining 5 electrons, right? Reduction is gaining 5 electrons. And then from there, notice that we already probably noticed that, but our atoms are balanced within the oxidation reduction couple. So everything is now just going to be multiplied to get to the same number. So what's our least common multiple here? 10, so multiply this by 5. So we deliver the 5s to our 2 acids here. And then we'll multiply this one by 2 and deliver it to potassium permanganate and manganese 2 sulfate. And then what else needs to be balanced? Where do you guys want to put in front of your? So we have 1s here, but we have 2 plus 1. So what do I need over here? 2. A 3, possibly. Okay. So 3 sulfates. Let's do hydrogens next. No, hold on. Let's do. No, that's already balanced. Potassiums are good. Let's do hydrogens next. So we see 5 from the first acid, plus 6, so we have 11, right? And then 5. You need a second. You need 3 here to get 6 more, right? So there's 6 plus 5 is 11. And then our oxygen should be naturally balanced already. 5, 2, 3, 2, 5, 3, 1. Good. Okay. So that's oxidation state balancing. Yeah.
Balancing the equation and not changing.
Balancing the non-redox ones.
Yeah.
The atoms that are not in our bracketed items is the last thing we do. Yep. So fancy way of balancing for really complex, like 8 or more compounds generally is what we do for this. Okay. So let's look at acid ones. Okay. So I wanted to look over. This is not acid. Hold on. Since we only got to do like 1 yesterday, I kind of want to walk through a couple of these, if that's okay. As a process overall, did you feel comfortable with your steps? Balancing your atoms, balancing your H's and O's. Okay. So I've got all my problem sets filled out, so this is the acid one. Yeah. Okay. So looking at your sulfate, or what's this 203? It's minus. Thiosulfate, okay, going to peroxydisulfate is what that's called. Okay, so we see our first half reaction. You have to break these into 2 half reactions. Your oxygen, your hypochlorite and your chlorine are going to come together as your second half reaction. When you look at the sulfurs in the first one, what do you notice? Not balanced, so I'm going to put a 2 here to balance the sulfurs out. That already kind of balances my oxygens out, right? So no need for waters here. So I've gone from half reactions, balance non-H's and O's. Balancing O's is kind of taken care of. Balancing H's is taken care of because there's no H's to handle. So now I need to account for the overall charge on both sides, then add electrons on one side or the other. So overall charge over here is what? Say again? So yeah, 4 negative, right? So it's a 2 times a -2. -4. Over here, a -2. So I got a I got a -4 and a -2. Where do I add my electrons? Thank you, Marcus. So then on this side, to decrease the charge, or the overall charge down to where the -4 is. So adding 2 electrons over here. Next one, chlorines are balanced, great. Oxygen here, what do I need to do? Add water on the other side to get an oxygen balance on this side. Now I've got 2 H's over here, so what do I do on this side? Add your 2 H pluses, okay? So now chlorines are balanced, oxygens are balanced, hydrogens are balanced. Now I've got to do charge balance. So I've got, what's my overall charge here? Say again? +1, so I got 2 pluses and 1 negative, so that gives me a +1 overall charge. And on this side, I have a -1 overall charge. I need to take that +1 down to -1 by adding what? 2 electrons on left or right? Left. So I'm adding 2 electrons here to reduce the overall net charge on this side down to what this net charge is over on the products. Now, what you'll always notice, and this is how you'll know if you're doing it right or wrong, is your electrons have to be on different sides. Because remember, one half reaction is representing oxidation, this one is representing reduction. So the first one is this one representing oxidation and reduction, just by where the electrons are. Wait, oxidation is loss of electrons. We're showing the loss of electrons by being produced. And then, so this other one is showing the gain of electrons by way of it being serving as a reactant, gaining in the reactant phase. So you can just look where the electrons are and easily tell if something's oxidized or reduced without assigning oxidation states. So now that I have this, I notice the electrons lost and gained are the same. So do I need to do anything else here? Yes. I don't do it. You don't have to, because the oxidation state balancing that we just did, we have nothing else to go off of. We have to look to see who's changing by reduction and oxidation. And the half reactions, which is why I prefer this one, you always just carry about the two that are similar. So like this thiosulfate goes with this one, and then I can do the process of balance the sulfurs, add water to balance oxygens, add H pluses to balance H's, and then look for charge balance. And the moment I add my electrons on one side, I already know that's the oxidation step, and this is the reduction step. So you don't have to do it. It actually you might spend more time than you need to. So once I see the
I got the oxidation one. Did you just go to the
well, did you balance it there like this?
I'm gonna do the first one. I did
Yeah, so it's whatever's left, yep. So it's going to be the other two that'll look similar. They have to look similar because you have to have some common atom that's being transferred from reactants to products, because that is the atom that's being oxidized or reduced based on what's happening. So now that we see our electrons are equivalent, we're going to add this up. So I already know that these are going to cancel because I can see they're equivalent, so I try not to carry things down unless I need to. So in the end, you guys should have had 2 thiosulfates plus 2 H pluses plus hypochlorite, and then peroxydisulfate and chlorine and water. So that should have been your final answer, correct? Who got this? Okay, you're working with me there, okay? Make sure you're writing this down. Okay, so let's go to the next one, to nitrate. So who's your first half reaction you guys went with here? Nitrate going to what? Nitrogen what? Dioxide, right? It's not an ion, don't call it ions, it's actually a compound. And then our copper solid going to copper 2+ ion, right? Alright, so looking at the first half reaction. Nitrogens are balanced, right? What's the next step? Add oxygens where? To the products, but how do I add oxygens? As water, okay? So oxygens come in the form of water. And then I have 2 H's over here now, so what do I need over here? 2 H pluses. Make sure your charges are written clearly so you can see your charge balance at the end. Okay, so nitrogens are good, oxygens are good, hydrogens are good. Now you have to do what? Charge balance, right? So what's the overall charge over here? +1, so it's a 2 plus and a -1, so it's 1 plus charge. Over here? 0. So 1 plus charge and 0. Where do I add my electrons? On the left, to the 1 plus, because you're going to bring the 1 plus down to 0. Alright, so is this one oxidized or reduced? Say again? Reduced, because the electrons are being gained. Okay. Next one, copper to copper 2. Easy peasy. What do? Add 2 electrons to the products, because the copper itself is being oxidized. 1 second. So now that I have half reaction 1 and half reaction 2, I need to now do what? Balance the what? The electrons, right? So balancing these electrons, I have 1 and 2, so who do I multiply? The top one by 2, and this 2 distributes all the way through the entire half reaction. So when I add them up, I'm going to have 2 electrons here and 2 electrons here. There should never ever be electrons left at the end, because we should be showing that they're the same ones lost and gained. So I already know I'm going to cancel those out, so I'm just not going to write it again. Okay? And then I have how many H's? 4 H pluses, and then 2 nitrates, and then 1 copper, and we're going to make copper 2 plus, and 2 nitrogen dioxides, and 2 waters. So we're carrying everything down on each side of the arrow. Question, Megan?
So in the acid-base populations, the oxidation state is not as important.
Correct. It's not important to the process, but it's important if I said, what's the oxidation state of copper? And you should be able to tell me that's a 0 and that's a 2. So identifying the oxidation states up front is not as important because you have a different method of solving, but you should still be able to identify them if it were asked of you. Okay? Let's go down to, which one do you guys want to do? 6? Alright, I'll go down to 6. Does anyone want me to do 3 right now? You okay? Oh, you guys did 1, 2. 3 is what I wanted to do in class. Let's do 3 together, alright? And then we'll go down to 6. I gave you half of what I wanted you guys to do, so it worked out. Alright, let's do 3 together. You picking up a little bit? Okay. Alright, so half reaction, what do you guys want to write? Be loud and proud for me, okay? What? Iodate, okay, I heard you. Iodate yields iodide, okay. That's our first half reaction. And then don't even try. Arsenate. I told you, we like memorize some of those polyatomic ions. There's hundreds more. So, and then perarsenate, because we have an extra O. Okay, so those are 2 half reactions. All right, looking back at the first one, what's your first step? Add what? Loud and proud? Add how many? 3 waters to the right side to balance our 3 oxygens. Okay, and then what? 6 H pluses to the reactant side to balance our 6 hydrogens. Okay, I's, O's, and H's are all balanced. Now do what? Charge. So what's the net charge over here? +5 over here. -1. So +5's got to go way down to -1. How many do I add? 6 electrons to the reactant side. Oxidize or reduced? Reduced. Okay, arsenics are fine. Oxygens are not. Where do I add water at? On what, the reactant side? I hope I'm not answering questions for myself. It's be pretty boring. You guys with me? Okay. Okay, so oxygens are good. What do I add now? 2 H's to the product side, and then now arsenics, O's, and H's are all balanced. What's my net charge on reactants? -3. What's my net charge on products? Say again? -1, right? So there's 2 pluses and a -3. So then, and I'm not writing the net charges up here. It's sometimes helpful to do that kind of to the side, so don't neglect that if that's helpful for you. But I have a -3 on one side and a -1 on the other side. Where do I add my electrons? To the product side. How many of them? 2 of them. So I got to bring that -1 even farther down to -3 net charge. Okay, so far so good. I've got to just now balance what? The bottom half reaction by multiplying by 3 to give an overall 6 electron exchange to the redox process. So here, I'm going to pull everything down for the moment, except for the electrons, because, they're gone. So the electrons are gone, because those will already naturally balance out. So I've got 6 H pluses, 1 iodate, 3 waters, 3 arsenates, yields an iodide, 3 waters, 3 perarsenates, and 6 H pluses. Whew. Alright, so it's big, right? What do I need to do now, maybe? Cancel things that are on the same on both sides. And you can reduce things. Like, if I have 3 H's on one side and 6 on the other, I can reduce those down to the lowest that I can. So I see I have 6 H's on one side and 6 H pluses on the other. So I'm actually going to cancel those out, right? So those are gone. Sometimes I'll put like a total X there just to make sure we know that's not there. And then, what else can I cancel? 3 H2Os on both sides, 3 H2Os. So, overall, remaining, we probably could have done this without balancing an acid. We could have balanced by inspection initially, but sometimes you have to fear that because you may not have charge balance at the end. So go through your process and then make sure your charge is balanced as well. Yeah.
Why did you multiply H2O?
I actually multiplied the whole, like this distributes all the way to all of these because I needed to have 2 electrons balanced with these 6 up here, so I had to make charge balance first. Yeah.
So you always need to take off the electrons for the 2.
If your electrons don't cancel, then you're wrong. Go back and figure it out. Okay. I think you guys said 6, right? All right. So I need a little space here for a second. Write down your half reactions if you haven't already. Oops, I don't want that either. No, put it down. Okay. Chromium 3+ goes to dichromate, and then bismate, something like that. Bismate. Okay, what'd you guys do first? Balance the what? Say again? To the 2 in front of chromium. Yep. You got to do your chromiums first, and that's probably the part that you guys miss. And that's usually the part most people like to neglect. So then now we can balance our oxygens. How many oxygens do I need, or how many waters do I need on reactant side? How many? 7. So 7 waters. And then what do I need over here? How many? 14 H pluses to balance out the 14 H's over there. What's my net charge over here? Which is a 6 or 3? 6 plus because there's 2 chromiums. And then over here, 12 plus. So I gotta get, where do I add my electrons? To the product side. So bring this 12 plus down to 6 plus. So taking 12 plus down to 6 plus by adding 6 electrons. Now that one's good. Next one, bismuths are fine. So what do I need? Where do I add my waters? Okay, 3 on the products, and then I add whatever here. 6 H pluses, Bi, O's, and H's are fine. Now I do charge balance. So net charge, 5 plus here, 3 plus. Where do I add electrons? To the left. So how many do I add? 2 electrons. So 6 electrons and 2 electrons, what do I need down here? A multiplier by 3 to balance your oxidation reduction electron exchange, and then add up. So I know the electrons are gone. I'm not even going to worry about writing those as are definite gone. So 7 H2Os plus 2 chromium 3 pluses is 12 hydrogen ions plus 3 bismuth polys. Where to say? Oh, my bad, guys. Thank you. Score for you guys. Okay. Okay. So then yields dichromate and 14 H pluses and 3 bismuth, 3 plus ions, and 9 waters. Okay. Are we here? All right. Take a second. Try to reduce where you can. That says 18. If you can't read that, scratch. Where can I reduce? Say again? So the hydrogen ions and the waters, right? So how many hydrogen ions do I have here? 18. How many do I have here? 14, right? Basically, we're going to reduce them as far down as we can. So we're going to get rid of all the 14. Those are out. But that canceled out only 14 of these, leaving me with what? 4 here. Okay? And then same story for waters. I can cancel out the entire 7 over here, but leave me with what over here? 2 waters here, because I'm just reducing as far down as I can. That's the part we didn't get to yesterday, was the reducing part. So just making sure you're okay with that. So the total simplified version of this is 2 chromiums plus 4 H pluses plus 3 BiO3, 1 minus, yields dichromate, 3 bismuth ions, and 2 waters. Alright, talk to the person next to you if you have a question real fast. Never done the math. We're going to do bases in like 1 minute, so if you need another question on acids, ask now. Alright, write down your instructions for bases. Write down your instructions for bases. Explain one more step. Okay, so since you got acids down so well, the base just has an additional step to account for the fact that there's truly no hydrogen ions present in excess when you have something in basic solution. So when you have something in basic solution, you have a lot of extra hydroxides. So we're going to go exactly the same method. Just at the end, modify one step with hydroxides. And as soon as I demonstrate for you, you'll be like, oh, got it, in low, it's just one extra step. Just making sure that your guys are fine with that. You can just do a couple practices. So when we add our hydroxides, though, 2 and H+, that will recombine to form water. So we'll have a lot of waters forming, and then we'll have a lot of canceling out and simplification of waters, because they basically, in the end, will probably be on both sides, so we'll have to make sure we simplify at the end. And I have 2 ways I'll do this, so you guys can kind of pick your poison, but I'll show you both of them up front so you can kind of see how that goes. Emily, if you want to go in the back room, it'll be quiet. We're pretty rowdy. Okay, so the last part right there was just simplify by canceling, but I think you guys probably assumed that was what we would do at the end. Right, give me a thumbs up when I'm good to go. We're finishing up. Okay, the first one we're going to do is just a single top reaction, which is on your base problem set. If you want to look at your base problem set, it's the iron to iron 3 or iron 2 hydroxide. So we're going to go from iron to iron 2 hydroxide. I can go back to this page if I need to. That one makes it more complex. So this is what we're going to do first. So just balance this half reaction as if you were doing it in acid. Okay? Just balance this half reaction as if you were doing it in acid. So you've got iron, yielding iron 2 hydroxide. What do you guys want to add? 2 what? Hold on. Balance your irons first, right down. Balance your O's by adding 2 waters. I just making sure I heard waters. So we're adding 2 waters over here. And then what? 2 H pluses over here, because I've got 4 H's over here. I've only got 2 here, so I need 2 H pluses over here. Okay. And then balance my electrons, right? So I've got a net charge of 0 on the reactants and a net charge of, say again? 2 plus on the product. So what do I need over here? 2 electrons. So that's kind of a second nature test. We can do acids pretty fast. So on this step now is where I'm going to incorporate that base stuff. I said to add, this was one of the most important points I highlighted, I didn't show you guys what that said, add your hydroxide number to basically cancel out the H+, but as soon as you add hydroxide to one side, you must add it to the other side as well, because you've already worked so hard to get this charge balance. And as soon as you add 2 hydroxides to this side, you've messed up your charge balance, right? So you must account for that by adding 2 hydroxides on the other. So I'm just going to add this kind of right underneath the hydrogen ion, and then my 2 hydroxides over here to account for that charge balance I already had. So what I can do now is combine. Now that I've added my hydroxides, I can combine these 2 to make 2 waters, because H plus and OH together come in to make water. Because I cannot have any free hydrogen ion, it's not an acid anymore, it's truly in base. So that's basically gone. I've got 2 waters here. So this whole thing is 2 OHs plus 2 waters plus iron yields iron 2 hydroxide plus 2 waters plus 2 electrons. But what else do you see I could simplify? The waters, right? So like I said, you're going to be simplifying waters a bit. So this water actually cancels with this water. So in the end, what I've actually done is I have 2 OHs, and I've added that to iron to make iron 2 hydroxide, and there's 2 electrons that help with the charge balance. So this looks really simple, and you maybe could have looked at the black text up here and just gone, oh yeah, I just need 2 hydroxides. Like, I know you could have done that. But what most people forget is to, at the end, add the electrons, because it's not what we've done all the time. So if I walk you through your steps of the process of getting to the addition of electrons, you'll never forget to add your electrons, because this is just a half reaction, right? We would have another half reaction that we would add together with that to cancel out the electrons at the end. Yes? Yes, that's what I want to show you. I think it's easier to do that cancellation up front, but sometimes I just hold things at the end and cancel at the end. That's really the two methods, either cancel early or cancel at the end, okay? So I'm going to move from this half reaction style to the true full reactions with the two half reactions embedded, okay? So this next one is the first one on your problem set, this chromate. You guys see it? Just going to get some space here. So write out your two half reactions first. Ooh. Okay, so that doesn't work for me. Okay. Make sure your charges are clear so you can see them. I'm going to leave some space between my two half reactions, so if I need to work in the middle of them, I can, okay? Just tips for your success. So you've got chromate, right? Chromate and chromium and chromium are balanced. What do you guys want to add next? 2 waters to the product side. Okay. What do you want to add next? Say again? 4H pluses to the reactant side. Okay. So chromiums, hydrogens, and oxygens are balanced up there. Look at your charge balance. Net charge over here. So there's a 4 plus and a 2 negative, so a 2 plus over here. 1 minus, so you have a 2 plus and a 1 minus. Where do I have my electrons? To the higher charge, right, to the positive charge. So how many am I adding here? 3 electrons to bring that 2 plus down to -1. Okay, so you just have to make sure you get to the point where you've added electrons and then you're good to now go with basic. So basic step. What do I do with, I'm still working with this first half reaction. What do I do for base? Add 4 hydroxides here. Am I done? 4 and 4 to the other side because I have to maintain charge balance. I just worked so hard to get there, I don't mess it up. So I've added my hydroxides. What do I do now? Combine these to make what? And I just usually circle them for myself so I know that I've combined them. There's 4 waters here, technically. There's no longer any free H plus. Okay. Anything else you guys want to do? Some people want to simplify the water. Okay, so what I might do here is just to help myself maintain my sanity, so I know what I'm writing. I sometimes will make this like a new half reaction just to write again, and I'll simplify by adding this one to this one and so on. Okay, so I'm going to write this again. 3 electrons plus, you guys said 4 waters here, 2 waters here, so truly what's left over? So these are gone, right? So there's only 2 here. It gets kind of messy, but you guys can simplify how you can. So we have 2 waters here plus a chromate yielding a chromium something and 4 hydroxides. Okay. So we just went to acid, went to base, simplified, got the half reaction as simple as I could. Yes? Now let's do the second half reaction. What do I need? 2 electrons on the right side, right? Okay. So then I have 2 electrons here. I'm sorry, I have 3 electrons in this half reaction, 2 electrons in this half reaction. What do I still have to do? Okay, multiply by what? Okay. So that's still a thing. I can't just ignore that stuff. That's why I say try to clean up your half reaction as much as you wish, and then we can do the comparison between the half reactions. So add that together for me. Alright, so I know you guys probably canceled your electrons out, right? So I just pulled them down this time to show you could, including the other things that we would simplify if we needed to. So your 6 electrons will cancel. Is there anything else that will cancel? No, so thumbs up. 4 waters? Yeah. So we did, but then we multiply by 2. Yeah, I have to, when I'm on the paper, I point to make sure I'm like distributing out. So on the board, sometimes it's rough, but yeah, 4 waters, 2 chromates, 3 sulfides, yields 2 CrO2 minuses, plus 8 hydroxides, plus 3 sulfurs. Okay. Try the next one. And then we'll stop with base for a minute, because I think if you can do it twice, I hope you can do it 1,000 times, but try the next one. And you guys can simplify at the end or simplify up top. It does not matter. Sometimes it's easy just to wait to simplify to the end. I might try that on this one. I'm just pulling all of it down to show segment. Prior to simplification, I'm just pulling it all down to show the segment. Alright, eyes up here for a second. So let's look at just half reactions for the moment, and I'm showing you the simplification at the end this time. If this makes you feel better and you prefer this as well, okay? So you went from your permanganate to your manganese dioxide, or 2-oxide as sometimes it's called. You added your waters, your 4H pluses, and then you added your 408. You balanced with charge of 3 electrons. You've added your 4 hydroxides and 4 hydroxides. You got that far. Okay, some of us probably went ahead and just said, okay, this is going to be called 4 waters now. So this is why my little box is there. I've actually utilized that as 4 waters. The oxalate goes to carbon dioxide, adding overall just a 2 on the carbon dioxide will satisfy your C's and your O's, and then your 2 electrons. We notice our electrons are not balanced, and you did a multiplier of 3 and 2. You got that far. Okay, so instead of simplifying so much the first part, I just pulled everything down just to show you could simplify at the end. So I've included everything, including electrons. So the 6 electrons that came down, the 8 waters, 2 permanganates, 3 oxalates, 2 manganese dioxide, or 2 oxides, 4 waters, 8 hydroxides, 6 carbon dioxides, and 6 electrons. 6 electrons will immediately cancel. What do you see over here now? I can combine or reduce. So I got 8 waters on the left, and I've got 4 waters on the right, correct? So I'm going to cancel out all 4 over here, and only reduce this down to 4 waters for the reactants. Anything else? No, right? We're good? So in the end you'll have 4 H2O plus 2 permanganate plus 3 oxalates, 2 2s, 8 hydroxides, and 6 CO2s. Are we good here? Yeah, I'm gonna stop for a second. So who prefers the first way where you simplified your half reaction as much as you could? Okay, who prefers just to simplify at the end? Or it's tomato. It really doesn't matter. You might find your groove later. So I'm just going to tell you a forewarning where we're heading with this. Guys, can you hold on for a second? Okay. So eventually we're going to have reactions where it's like, hey, you have potassium permanganate and you're titrating it with oxalic acid. You've added such and such milliliters of this molarity and such milliliters, find the molarity of your potassium permanganate. It's a titration, right? So what you would have is a reaction. You predict the products, or I'd give you help to say like Mn2 plus ion form. So you predict your products, you do your half reactions, you go through balancing, and I would say in the process of the titration, like this is acid catalyzed or this is base catalyzed, and you would know which way to balance it with acid or base. You go through your whole process, you balance, and you get down here. And then you would start the stoichiometry. That's where we're going. It's you balance it yourself first, which normally we do. Normally we balance. I mean, that's just what we have to do for our reactions. This is just another like style of balancing. And then you start your stoichiometry. So that's what's coming next. We're doing redox stoichiometry if we can tomorrow. Okay? Questions on bases right now? Yeah. On the reactant side? You didn't pull anything in this half reaction, did you? Like you didn't pull anything else into it. Is that all you have? Miriam, look over. Look it up. I want you guys to try one more by yourselves, okay? The third one. So we just did 1 and 2. Try 3. I'm a little behind. Oh my gosh, this is a beast. I didn't simplify at all yet. Hold up.
Now we just need to multiply it just changed the
The blue work is the answer. I simplified at the end. I simplified beforehand. It does.
No, I know it is wrong. I just need to put it to.
Yay! Alright, stand up if you got the blue. Stand up. Oh, no, you got to have the blue. You got to have the whole blue. Stand up. Or 5. Okay, I saw me. No, okay, thanks. Take a minute to review what you did. Okay. So I had something else planned for us, but I don't think we're gonna get to that yet. So here's our next plan. Okay. So you guys can practice more of the problem set, acid balancing and base balancing. Don't do any more of the oxidation state one. But that will be like 1 in 10, right? You'll primarily see acid. That's probably like 6 out of 10 times we see it, and then base is 3 out of the times that we see it. So just be very comfortable with acids and bases, and then the oxidation state balancing will come in as needed. But I will always prompt you to say, this is balanced in acid, or this is balanced in base, so no guesswork here, okay? It's going to be very well told to you. All right, so here's your next assignment. I Googled Docs to show you too. So I want you guys to create a poster or a public service announcement about why redox is important in real life. You have to select a focus. That focus needs to be something that's meaningful to the general population. Remember, not everybody cares about chemistry as much as you do, but make sure that you can easily communicate that information. So you can choose, these are just some of the examples: consumer chemistry, food chemistry, pharmacology. I had people talk about marijuana last time, so just make sure that you're trying to be as PG-13 as you can. This will take the form of a poster, okay? Explain to the community about that chemical reaction that they should be or may already be aware of. And one of the broad topics listed above, or etc. If you have another topic, that's fine. List the chemical reaction along with any common names, because most people may not know, like acetaminophen is Tylenol. Like, try to give them some common names on top of the chemical names themselves. Give the information on the redox reaction, so you should be able to tell me like what things are being oxidized or reduced, or who's the oxidizing agent, who's the reducing agent. Try to incorporate some of the terminology. Explain the importance of understanding that, like, to the general consumer of information. Remember, go deep for me, but try to leave it so you have 2 levels of information on your poster, and then make sure that it's pretty. Okay? You can be in groups of 3. Select. The groups of 3, I think I might have 1 group of 4. Yeah, I'll have 1 group of 4 because there's 25 of you. Somebody needs to claim Emily. You need to brainstorm for the next 10 minutes. Brainstorm for the next 10 minutes. Alright, go to the lab station and sign over your lab group, your project, or activities, So, 5 groups of 3. Math. 1 group of 4. and 7 groups of 3. Yeah. Longer before and 7 groups of 3. Longer before and 7 groups of 3. Brainstorm, join on that topic. We'd like to get on and I don't know when this is due yet. I'm just telling you right now the assignment. Can you go back to us? Now, on the video, you'll see me canceling these out. It'll be a little bit easier to see. All right, guys, listen. 3, 2, 1. You can scroll back up and see the instructions, but I'm going to keep this on the bottom. I want your group name and your topic, if you can, by the end of class. First come, first serve. So make sure that you get your stuff up there. Write down what you need. They already did. Yeah. You four. Four work together. They're in the, she's in the.
Like when you say topic, like one of these, or like
it can be more specific. I'm just giving you broad category to help you narrow your focus. So can we just write down the broad category for now? Yeah. And then you can just put dot. Just put dot. Because other people will choose different. Yeah. I'm sorry. You guys can all choose the same broad topic. Okay. So, food chemistry, put dot. They're gonna narrow from there because food chemistry is like everything, right? So you can put your broad category up there until you get your specific. Just put dot. That means like your something.
you said Marcy? Like your name, you know? Are we good? Group name locked down.
Chromosomes.
Oh, what is it?
Scroll up. Is that what you said?
Well, up was like previous
Margaret, there's a line.
Oh, we've been.
Oh, there's a line.
Yeah.
What is it? Environmental cheese farming, technology, chemistry.
What's by the bomb?
Pretty sure.
Atomic?
Can we treat the same broad topic if we have
Absolutely.
Okay.
Alright.
Yeah, it's like, I'm gonna stand up inside, but I don't want to let it. And then it's gonna rest on or. There we go. Let's do it now.
Two L's or one?
No, wait. I wasn't saying that. It was
Yeah.
Like 3 minutes with you guys.
I'm not going way back now.
Alright, unfortunately, you have to put your laptops up in a minute. Time flies. Oh my gosh, thank are awful. Why would you put that up there?
I didn't make it up. I agreed to it.
Are you not like
Oh, is that like a pre-film?
You get a razor? Let me get it here. Let me get a little eraser. Pause for me. It's because there's a pin.
Can we email you tonight, right there? And like the top.
Yeah. Hold on, Cass. Give me a second. ASAP. Erasing this.
yes. Thank you.
Sorry. Alright, laptops up in a minute, please, and thank you. I like it, yeah.
Is it first plus that you can't actually find stuff for atomic bombs? It's classified.
Is it classified? Alright, okay, hold on. Let me, can I get you guys to just a second?
Yeah, it's
Alright, can I get you guys the address in just a second? Okay. Alright, guys, come back up here ASAP. I gotta show you one more thing before you go. Email. Okay, just drop it right there. In what?
She was just like, yeah, Reese keeps herself I can't keep myself.
All right. As you come back to your seats, I'm talking to you. Okay, so you've got to be quiet. I got like a minute, so pack up like ninjas. I don't want to hear you or see you pack up. Just pack up. All right. As you pack up with one eye down, put one eye on the board for me. And I just wanted to show you this awesome website. If you go to compoundchem.com, or if you just Google compound interest chemistry, they've got a ton of infographics that might give you some inspiration, like atmospheric chemistry, aroma chemistry, biochemistry, chemical warfare. Somebody just asked me about atomic bombs. Fun question for the day. Cosmetic chemistry, things that people care about chemistry, environmental chemistry. Like, you can click on any of these and you can see awesome stuff. Like, lots of things that would give you ocean acidification. Like, everybody cares about mammals in the oceans, right? Oh, my bad. The whole time I'm showing you things. Go do work. Bye. Like, think about what you're going to do your posters on, and do PSA, or do a little bit of PS. I'll update the website. Nobody told me it was frozen.
I'll try to come in.
Okay.
I don't think this is full time.